All right, welcome everyone. Welcome to LinkedIn. Welcome to Stream Processing Meetup. It's great to have so many people here in person, and we have our participants attending this event remotely over Zoom. So welcome to LinkedIn. Welcome to Stream Processing Meetup. So today we have three exciting talks, three exciting sessions from DoorDash, Feldera, and Voltron Data. Here is the agenda. So first, I'll go over some FAQs. Then we will have our first session today, which is Unified Streaming Framework, a declarative real-time streaming framework for Flink Spark. Then we will have the streaming queries without compromise, our second talk. And finally, we will have Ibis, the portable Python Dataframe API. So here are some frequently asked questions. Are the talks being recorded? Yes, we are recording the talks, and they're going to be posted on YouTube by LinkedIn Engineering in LinkedIn Engineering channel. The Meetup event site will also have the link once the recording is available. How can I ask questions to the presenters? So first of all, if you are in person, at the end of each session, we are going to give chance to our participants to ask questions. And Boris here will pass the microphone, and once you have the microphone, you can ask the question. For our remote participants, we have the Q&A tool on Zoom. So using this tool, you can ask your questions during the session. At the end of each talk, presenters will answer the questions. And depending on the time and the number of questions, we may need to cover some of the questions. After all the talks conclude, our speakers may answer these questions asynchronously. I want to present whom should I talk to. There are a couple of options here. You can post a message on the Meetup site. You can send a LinkedIn message to me. I'm Adem Efegencer, or our other co-hosts, Gary or Boris or Beckett. And here are our email addresses. You can also send us an email. And with that, I'd like to introduce our first session speakers. So this talk will be on Unified Streaming Framework, a declarative real-time streaming framework for Flink and Spark. And our speakers are Bashar Onat and Chen Yang from DoorDash. Bashar is an accomplished software engineer specializing in real-time streaming platforms. At DoorDash, he works as a software engineer on the real-time platform team, focusing on the real-time metrics platform. Bashar also contributed significantly as a software engineer at Meta, handling large-scale data workloads with the Presto team. Prior to that, he played a vital role in bootstrapping the real-time platform at Stream. Chen Yang is a software engineer in the real-time streaming platform team at DoorDash. His focus is on building the streaming processing platform and real-time related products to power DoorDash applications. With that, I'll leave it to Bashar and Chen.
Hey everyone. All right, let's start it. My name is Chen. I'm here with Bashar, which we are all both from real-time streaming team at DoorDash. So we want to present the unified stream framework. Start it. So this is the agenda. We will basically talking about what is the stream framework, giving some context about how are they doing at DoorDash right now. We will also discuss about our product vision, why we want to build in this framework, and also give a high-level introduction about this framework, talking about the high-level vision we want to achieve, and also explain some example use case. And later, Bashar will talking about what we already do right now, and also the example job config. And also, we're talking about reliability, the future works. All right, so streaming framework at DoorDash. So right now at DoorDash, we have two streaming frameworks. One thing is the Flink. I think it's well known for everybody here. So for Flink, we actually already building a big data ingestion pipeline based on Kafka and Flink. We have been using for DoorDash for more than 4 years now, which injecting billions of analytic US data. We have integration with data warehouse like Data Lake and Snowflake and also Iceberg right now. And also we have building a very high level abstraction layer for the Flink application, which your user basically can define a job config and then just writing a SQL-based DSL language to do the actual computer logic. And for Spark streaming, this is very popular right now at DoorDash as well, especially for our data engineering. Because they have well support material tooling using a notebook, and also they have well integration with the data lake like join, merge. These two framework which existing at DoorDash and which actually leading to a lot of questions from our clients. So basically, people are asking like, okay, which stream framework I should use? And based on the stream framework, if I know how to write Flink application, how can I easily migrate this same logic to Spark streaming? So this leading to us, like we're thinking about how we can help our client to solve this problem. Can we providing a stream framework which actually have high-level abstraction of both streaming framework, which can help user easily to define what is the source, what is the sink, and how we can easily to processing the data without knowing the details of the Flink infrastructure. Yeah. So that's why we building the unified stream framework. All right, so we want to providing a high-level abstraction layer of the framework, which you can underneath running both Spark and Flink. And also we want to ensure like the vendor neutrality as well as reliability, and also which we can utilize whatever we already building for DoorDash with for all the streaming framework, like for example, how you can manage the schema, how you can do the serializer, deserializer easily. Yeah. So this is the high-level vision of our framework. So basically, you can see like we want the user come to a one entry point, define your job, define what is your source, what is your sink, and then just write a simple logic like using DSL-based language, for example, like SQL, writing about the computer logic, and you submit the job. And underneath, the job can be running on Flink for Kubernetes, and also it can be running on Spark for EMR or Databricks. So I'll just briefly talk about this. Basically, some use cases we are building this framework for. So many is basically for us to easily generate the personalization attributes for DoorDash. For example, like we want to know if a user is a Dash Pass, we want to provide different promotion, and also we can provide in session, some insight based on the user's search history. We are updating the feed ranking. Also, we are updating the search ranking based on the purchase history. Yeah, this is basically the use case I'm just talking about. So you think about this graph here. This CockroachDB is basically how we are serving our features to application. In order to generate this personalized feature, for example, the Dash Pass status, also the last 7 days orders of each customer, right now we actually have to write 2 jobs on 2 streaming framework. So one is building on Flink, which actually handling, for example, the Dash Pass status change. Like when users subscribe to this Dash Pass status, we want this data to be reflected in our system in less than 1 minute. So basically, the application can reflect the change, like giving some promotion based on if you are Dash Pass. So we have to do it using Flink. And meanwhile, we will also want to provide in some features of, for example, last 7 days order, which actually we are writing a Spark job right now, which consume the Kafka and then aggregate the data with Delta, which had all the historic data, and then generate data and send to CockroachDB. So it's kind of like, feel it's a difficulty here. Like people have to write 2 different streaming jobs and understand all this difference, and also need to maintain this operation and also deploy this job. And what we're trying to do now is like for Flink, we already have high-level abstraction layer, which user can just define a YAML config and write a DSL job to define a Flink job. We are doing the similar thing for the Spark as well. For the Spark job, you don't actually need to write the code as well. Just define the job config with a source, output, and then define your computer logic based on DSL. And later, we want to combine both this YAML definition and DSL definition with one unified format. And then underneath, people count our endpoint submit the job. It can be run to different framework, like different streaming framework, Flink or Spark. And then we can just achieve this with a very easy onboarding process. All right, I will hand over to Basha talk about the details.
So where are we now? So current state of the USF framework, essentially, that we built. So we right now have, as my colleague said, essentially we have the Spark streaming that is running on Databricks. This is running on open source Spark, and this essentially have a we run these jobs through the complete orchestration service with having this auto remediation in case there's some incident or issues occur. We established a YAML and essentially SQL-based templatized job config. We have various sources like Kafka and Delta, and we can write to Delta and CRDB. So onboarding, as we talked, like we have YAML and SQL-based combination of onboarding that we do, and job deployment happens through a RESTful endpoint. So we have all the metrics that we keep track of for like health of the system, and we have SLO-based alerting for these jobs. So how does it look? Both Flink at the bottom and the Spark at the top. So the user comes in, so essentially like for this example, and they have like a Kafka, and they essentially send those events to, if they pick up Spark, it goes through the source streaming table, then after that goes through the deserialization and SQL transformations. And after that, the final transform data goes through the sink, and that will be written downstream into either essentially CRDB and Delta. Similarly, in the same logic, same Kafka goes through the source streaming table and deserialization, and after that, there's a one SQL, and then final transform result will be written to a sink function, which will go through the CRDB or Kafka. So essentially, the job definitions are same. They're YAML and SQL efforts that engineers need to write to just get the job running. In this example, Flink runs on Kubernetes ecosystem, and the Spark runs on Databricks. So going on to the onboarding, how the users onboard to this system, essentially. So there are two paths as of now, and one path is essentially how we have a self-serve UI where users will define. This is for Flink path, where they will create the YAML and the SQL definition on the UI with the guidance and help. And after that, essentially the job will be written into the job repo. And after that, using the control plane, the user will be able to submit the job, and that will deploy on the Kubernetes ecosystem that we have. So for the Flink version. And the four other path, which is a Spark version, user defines the YAML and SQL that will be written into the job config repo. There's no self-serve UI as of now. That will be then after the user will call the control plane to deploy the job or terminate the job. And after that, that orchestration service will take care of the deployment onto the Databricks ecosystem. So going over to some examples of the Spark version. So in the Spark, if you see where I highlighted red, the top item is Kafka and Delta. This is where your source and destination is. And after that, you give information about your Kafka connection, and also the Delta information about which table that you're writing to. And then after that, the next part is about the parameters for you to deploy the job, which kind of instances that you wanted to use, what's the essentially pod count you need, and what's the memory requirements that you have. And after that, you define two things. One of them is the source SQL, another one is a sink SQL. Source SQL is generally the serialization part where you define essentially which fields are important to you from the source that you receive. It's more flattening essentially the fields that you require. And in the sink SQL, you generally transform your results into the format that you want. Similarly, going on to the Flink approach, it is similar YAML format. So we have a source, they define at the top. They have we have a Kafka source. We define which cluster, which topic, which schema. And after that, there's a SQL line in there in line. And there's a resource configuration that we establish for how many task managers or memory that you need. At the bottom, there will be a sink, where in the sink, essentially, you define which destination that you want to write. Is like a Kafka? Is it a CRDB? You define that. And for this example, we picked the CRDB sink, where we define how many, what batch size that you're writing into, what's the interval, and all these stuff. These are standard configurations. And in line SQL is an example I give on the right side. Essentially, you do just define whatever that you define on the source. You use that as your source to transform your events. So coming back to the reliability part. So as I said, we have dashboards for both approaches, Flink and Spark, and we have metrics for availability and data freshness. And based on that, we essentially established SLO dashboards, and we track it very aggressively for the users because users have very tight expectations for the availability and data freshness. So this is where we are and what is next. So what is next is essentially we wanted to update the YAML definition to handle multiple sources in sync and also cohabitate with existing Flink framework, because right now they're like YAML definitions are a little bit different and it only supports one source to one destination. So we wanted to enhance that to improve capabilities like enrichment cases and all these stuff, which is very useful for many users. And also enable support for running the Spark on EMR, because we are like so like tied into the Databricks for now, but our orchestration engine actually offers like running on EMR as well, which we need to invest on whether we have any problems. Given the open source version, I don't think we would have so much issues. We're not vendor locked in our design, but we need to verify. The third thing is we have users, as my colleague says, we have a lot of the users of the system, which have a lot of Python UDS, Python functions, custom logic that they wanted to integrate. Now we are looking ways to how we can integrate without breaking the whole framework approach, because we don't want to do custom things. We want to establish a good framework that can sustain for a long time. And also this comes down to, again, standardizing the YAML definition for Flink and Spark so that we can be easier for user to transition one to another one. So if any other standardized sources and syncs, like let's say tomorrow someone says we need to write to Postgres, like one example, we need to be able to support them. So we need to add new sources and syncs depending on use cases. And I think going on to onboarding part, we have right now immediate improving on the job testing and exploration using the notebook. We right now do not offer that. It's right now tested on you run on your dev environment or something essentially, and you see the results, and based on that you essentially iterate. It is a little bit iterative by slow. We wanted to improve based on integration of notebook. And also, as I said before, Flink has a self-serve UI, but Spark Path doesn't have that. We need to add that also to make sure that user have one experience for onboarding to the system. So essentially, that's what we're going to focus on. And finally, I think we didn't talk about the data correctness, right? So in this SLO definition, we wanted to find a good way to establish that for the jobs that we have. Right now it's a bit like hard because of the customization, but I think that could be doable. I think we need to integrate with existing frameworks within DoorDash to essentially establish that in the long run, I think, or we will build some established categories of the job that maybe like have data correctness achieved. So that is all from ours. And is there any questions?
Hi, my name is Antriksh. I had a quick question on, I think, your second slide regarding the SLAs between Flink and the Spark job, maybe one before.
Are you talking about this?
Sorry, if you go back, you kind of mentioned the two approaches,
right?
The two syncs, and I believe either even one slide before this, please. Just wanted to know, I think one before this. I'm sorry.
No problem. So
it was much earlier. Yeah, like right in the beginning. Maybe one before this, but I just wanted to know, like, how. Yeah, right. The freshness.
This one here. I don't know.
Doesn't matter.
Here. Probably.
Yes. There we go. Yeah. So, how is or why is Flink? Why is the freshness like less than 1 minute compared to your Spark streaming jobs?
So that's, I think, a good question, and I think I can answer for this one. So because the expectation from the Spark is like we enable a large window aggregations that we had to do, like as my friend said, like the last 28 days, and this on a large scale, we needed a trigger window about essentially 1 minute. So that just kind of pushes us into the territories that Flink can handle, obviously, but Spark cannot. So that's why we kind of put a cap there. Obviously, the aggregations can get really, really complex, as you would know. In such cases, we kind of put a 5 minute as a top line item where this is business use case driven, but also in a way, given the SQLs can be complicated, it can really cause like a up to 5 minutes delays based on the large volume that people are trying to churn into to build those real-time attributes that we were talking about.
So it's primarily due to just the join, right? Like because you're joining as the Delta data.
So we do have join cases, but we have also raw just transformation cases as well. So we do have both.
Okay. All right. Thanks.
You're maintaining the YAML files on two different places. have you considered using Apache Beam? I heard.
Yeah, I think I'm laughing because of like some historical context, but inside joke. But we actually considered, but I think we were trying to go for a much easier abstraction for the users, and that would mean like essentially users like even don't have a context about how to build those SQLs, how to build those YAML. You want to actually help them. So actually, if you go to the self-serve UI of the Flink approach, we have builders of the how to build a query, so people don't know it, they can easily build those things. Streamline is like checked validations happen in this opening essentially when people submit their jobs. Here with a Beam, you have to know a lot of things by hand essentially.
Hi, thank you for the presentation. Could you go back to the slide where you had an example of the YAML file?
Yes, I'll find it. This one?
Oh, yes. So I was wondering who would be writing all of these specifications, and given that there is a lot of like resource provisioning requirements, like does your control plane also do like optimizations of these resources, or how does that work?
So I can explain. I think that comes down to the same question that this gentleman has. So for this, people actually technically don't write this. This is an example output that we have coming from the self-serve UI, an example. So right now, as I said before, Spark doesn't have that self-serve UI option. So given that people need to type it by essentially either like copy pasting or like essentially having their templating build logic. But our goal essentially with the future, which will have a self-serve UI, which this automatically will be filled in and user don't have to know all these configurations.
So does that mean that it analyzes the query and decides like how much, like for example, memory we need?
Oh, that I think comes down under the auto remediation discussions. I think like we obviously for the Flink size, Flink essentially we have some short sizing model essentially that we established. That is like I think very industry standard. I think, and you can increase if you want to. That's option given to you on the UI. For the Spark, I think we'll follow the same logic. But I think one thing I know is our orchestration framework that we are leveraging in the first Spark. It actually has a capability of understanding the requirements, and they can add essentially or change scale. That's the longer vision of the orchestration framework that we are leveraging.
Let's have a couple of questions from online.
So the first question is from Yi Pan. The YAML plus SQL authoring experience is very similar to DBT. What's the difference between USF and DBT?
I'm not well versed with the DBT2 claim, but I think from the high level I know, maybe I can tell. I think it's a standard that we essentially established within DoorDash, like from the Flink standpoint, like many years ago. So essentially, we wanted to keep that experience to the like essentially other frameworks as well. So that's why I think we went into that approach to not alienate the users. So in that point, I think it's more of a familiarity that we picked. But I think like DBT, again, I need to look into to claim any response to it. I'm not going to lie on this.
Next question is from Kitu. What are the challenges you face with this approach? When does it break, and how did you solve it?
Okay. Yeah, do you want to answer? No? Okay. Yeah, it's a lot. Yeah, so I think we had to go through, like, I think given the Databricks ecosystem is a little bit vendor lock-in, quote unquote, we had to tread very carefully on open source, picking open source libraries for the Spark. That was actually one of the challenges that we had to face. We had to learn how to navigate around that roadblocks when we were like essentially leveraging any library, because sometimes we put a library and just library requires some Scala version that breaks the whole ecosystem. Some people I think are like familiar with this, so that's where we I think had to iterate a lot. But I think at this point it's very stable, but obviously, and we have good checks and balances in the system. But I think overall we still have like miles to go essentially on this.
Next question is from Shin. What's the relationship between USF and Beam?
I think I answered that question. Maybe I should not again.
Yeah. So next question is again from Yipan. What are the feedbacks from the users with respect to expressiveness of the YAML plus SQL API compared to Java, like Beam?
So from my experience, especially I can talk for the like Flink side in like I think in many detail on this point, because I like using this and develop the self-serve UI also effort. I think the YAML is complicated for a lot of people who are working on the product side. And for that, self-serve UI is a must. So for people who know, like power users, they might essentially enjoy this YAML definitions and all. But what we found is like for faster iteration, definitely like a UI is a must. So yes, the feedback we get for Flink at this point is great because we have self-serve UI, but for Spark, there's some challenges. Luckily, our users are engineers like who are working in infra side closely. So, but I think if we expose it to product engineers, their behavior probably would be different, I can tell.
So last two questions. Yipan asks, for the Python driver, why is it only for Spark side? Won't you need it for Flink as well?
I think, yeah, that's a good question. I think the Python side is, I think, because of the existing libraries within the company that people build and leverage, they wanted to essentially transition into the USF ecosystem for, and that was the reason for that. And I think the people who work on the Python essentially based code heavily involved in the Spark ecosystem more than Flink also. So twofold. So they're like, I think, invested also in PyFlink. They're like interested in exploring that area. But I think the use cases that they're looking for is not there yet. So from what I can say.
Question is from Frank's son. Are the use cases all centered around personalization and growth? What other use cases have this address?
I think you skipped the sessionization also. Yeah. So one of the other use cases that we completely lost over is like the sessionization. So we also analyze the user session information, which is like very common use case for a lot of like web-based companies. So that's also another area that this infrastructure is going to be like is already used, but I think we're going to go for more integrations with this user session data to enhance the experience for the I think understanding how the user behavior is essentially.
Right. Those were all the questions. Thank you, Bashar and Chen.
Thank you.
Good evening, everyone. My name is Boris Kolnik. I'm co-host with Efe. And the next speaker, they will be talking about streaming queries without compromise. Mihai Leonid over there. And so Mihai is chief scientist at Feldera. He has a PhD in computer science from Carnegie Mellon University. He was previously employed at VMware Research, Barefoot Networks, and Microsoft Research. Mihai has worked on configurable hardware, computer architecture, compilers, security, distributed system, big data platforms, large-scale machine learning. And Leonid is a CTO and co-founder, holds a PhD in computer science from the University of New South Wales. Before co-founding Feldera, he worked as a researcher at NICTA, University of Toronto, Carnegie Mellon University, Samsung Research America, and most recently at VMware. Leonid has published dozens of research papers on operating system, programming languages, formal verification, software-defined networks, and databases. Go ahead.
Hello. Thank you all for being here. I also want to thank the previous speakers for having such a short talk because I really had trouble squeezing these slides. So I'll take advantage of the extra time. All right. So what is this about? Well, if you look in the industry, there's a dichotomy. There's streaming systems and there's databases. And people have been talking a lot about how this could be unified. And I think something is in the air. But I think I'll show you today how to think about this properly. So I think these two systems are accidentally distinct, these two classes of systems. They are unified. So, and database and streaming systems are just different facets of the same object. And one thing that ties them is incremental view maintenance. All right, so there's some documentation you can read. We wrote some papers. One was in VLDB last summer. A second one is a simplified version, which we wrote, so it's more accessible, less mathematics. but also there's code. So on GitHub, you can see all of this under an MIT license. So it's not just theoretical, it works. Okay, so what I think is most interesting about this stuff is the way to think about databases as a streaming system. So let's start from this problem. We have a database, and the database evolves over time. So we have a database, and then you keep changing it. Time goes from left to right. And usually your databases tend to be large these days, but the changes tend to be small. And then the problem you have is you have a query that you keep wanting to reevaluate over and over this database. Usually this is done using views. So if you define a view, what this means is that every time a database changes, your view should be updated. So for each instance of the database, you have an instance of the view. Now, what is incremental view maintenance? Incremental view maintenance, instead of recomputing the query about the database every time it changes, it will actually compute the changes to the view and apply them to the previous version of the view. And because the changes are much smaller, usually the database changes are much smaller, usually also the view changes tend to be much smaller. And what you would like to do is the following. You would like, instead of computing the queries using these green arrows, which run over the database, you'd like to run the queries over the changes, which are these blue arrows. And this is what this talk is about. I will show you how you can do this for any query, essentially you can write. So we call this Q delta because it's a query that computes on changes. But these are not usual queries. You have to, in order to solve this problem properly, you have to think of them as streaming systems. And this is desirable because we hope that the blue queries are much cheaper than the green queries. Oh, by the way, if you have questions, I'll be happy to take them online as long as they're not too complicated. I mean, online during the talk. Okay, so we'll be using these data flow graphs. This is think of them as query plans. So these boxes are various operators in your query plan, and arrows show flow of data. All right, so I think this is, we've seen boxes in the previous talk too. All right, so now let's talk about streams. Streams, there's many ways to think about streams. In this talk, think of a stream as an infinite vector that grows with time. It's indexed by time. So this is a stream, it goes from right to left. And the 0th element is 1. It's a stream of integers. So for any data type A, you can have streams of values of the data type. And we'll put a condition which you might find bizarre, but we want the data on our stream to have a plus and a minus. And the reason is that if you have changes, you must talk about computing differences, which are minuses. And if you want to apply changes to an object, you need a plus in order to compute the new value of an object after a change has been applied. And we also will require these values to form a nice algebraic structure, a commutative group. Don't worry about it too much. It works. Yeah, this might be look artificial, but it can be made to work in practice very, very well. Okay, so now I will depict. I showed you boxes and arrows. The boxes were computations. They would take one value and emit a value. Now we also want to use computations over streams. And we show streams using arrows with double headers in this presentation. So T is a binary operator. So we call it an operator as to distinguish it from a function. The function takes only a value, whereas the operator takes a stream. But still, boxes are computations, and the inputs and outputs can be streams. So this T takes two streams, I and J, and emits another stream. All right? I think so far everything is pretty clear. So now how can we build stream computations if we only have functions? Well, the simplest way is to do something called lifting. And it looks hard, but in reality, it's actually easy. It's hard for that guy. So let's say you have a function that takes a value and emits a value. The lifted function is transforming this computation into a box on streams. So you simply apply this function to every value in the stream independently, right? So that's what your output is. I think it's pretty obvious. It's like the map, in MapReduce, for example. Okay, now let me show you an operator which you cannot write using lifting a function. It's a really simple operator. We call it delay, and it's written z to the -1. So by the way, this formalism is inspired by digital signal processing. So the DBSP comes from database as a signal processing. And the notation of delay using the z to the -1 comes from digital signal processing. So if you happen to ever do a digital signal processing, this will look familiar. But don't worry about it. So when you see a z, read as delay. So what does a delay do? if you're given a stream of values, the delay will remember the values. First, it will emit a 0, and then will emit the values that it's seen previously. Okay, so just emits the values one clock cycle later than they showed up. So this requires this operator to have memory. It must remember what it's seen and emit it a little later. And in our framework, this is the only operator that has memory. So we'll build everything out of operators which are stateless, and this is the only stateful operator. Okay, so now we have 3 ingredients. We have functions that we can lift, we have delays, and then we can have circuits which put things together. So let's build some interesting stream operators. So look at this one. So what do? We take a stream S, then we delay it, we negate it, and then we add it to itself. Anybody want to venture what this does? Right, somebody said delta. So if you write, the teeth output of this operator will be the current input minus the previous. So it just computes deltas. If you're giving a string of values to this operator, what you'll get at the output is the sequence of deltas within consecutive inputs. So we'll denote this by D from differentiation. This is really like the differentiation mathematics. It sounds scary, but it's just a minus, right? And so look, there's an example. If you give it 1, 2, 3, 2, you'll get 1, 1, 1 minus 1. So from a stream of values, it will compute a stream of changes. Okay, very, very good. Now let's look at another operator, which might look even simpler because it has only 2 blocks. It has a delay and a plus. So it's a little bizarre because what it does, it uses its own output in order to compute the output. So, but it's well defined. Why? Because this delay can actually give you an output before it's seen any input. So anybody want to guess what this is computing? That's right. Excellent. So we can actually just do it step by step. The first output will be the same as the first input because from the bottom comes a 0. Then the second then another output will be the current input plus the previous output. This is what it means, the delay says the previous output. So if you spell out this, what you'll see is that the teeth output will be everything you've seen so far added up. And this is actually called integration. And it's the opposite of differentiation. So if I give you a stream of deltas, so this is the one we computed on the previous slide, and you feed it to this operator, you'll get back the original stream. It's very simple. See, only 2 blocks, and yet it does something very interesting. Okay, and now these 2 operators, as I alluded, they cancel out. If you put them in sequence, you get nothing. This is an interesting property which will be very useful. Okay, so now let me make a statement. Every database you've used, MySQL, Snowflake, Postgres, they're all streaming systems. And let me explain why. So let's take a database. What is a database? Just a set of tables. And now, what is a transaction? A transaction is a change that you apply to your database. Okay. Now, transactions have this beautiful property. This is one of the fundamental things that database theory has brought, is this idea of serialization. The transactions, no matter if you do them simultaneously, concurrently, in the end, they will execute in some order. And this is the order of the transactions. These T's are the transactions. So they form a stream, right? I told you, an infinite vector is a stream. So think of this, the transactions as forming a stream. So T of K is the K transaction that you apply to your database. Now, corresponding to this stream of transactions, you have a stream of snapshots of your database. DB0 is the original database. Then you have the database after you've applied the first transaction, the second one, and so on. So for each transaction you apply, you get a new database. Now it turns out that you can make a very clear relationship between these 2 streams. They are related by this integration operator. The third database is just the result of applying a sequence of the transactions that you've seen so far. So this is a diagram, and this is exactly how databases work. Databases are just integration machines. They take the changes you supply, inserts or deletes, and they apply them to tables, and the tables are the integrals of those changes. Okay, in general, database is the integral of a transaction stream. Okay, now what is a view? So let's take a query defining a view. What does it mean? So you have, as I said, we have a stream of databases. These are the snapshots of your database you've seen. so far. So when you define a view, what does it mean? It means that for every version of the database, you have a version of the view. For the first database, you have the first view, and so on. And how is this view computed? Well, it's computed by applying the query to the snapshot of the database. But this is exactly the lifting operator I've described before, right? So this view is a stream. Views are streams of snapshots. Databases are streams. Databases are streams of snapshots. And queries that define views are just lifted functions that are applied to the database stream to produce the view stream. All right, now let's put things together. So I will show you what incremental computations are on databases. So this is the same picture as the previous slide. So you have a lifted query, which defines the view. Oops, I don't know what this means. Okay, now, I guess it was an important point. So remember, the database itself is the integral of the transactions. I did nothing but put together the two pictures we've seen on the previous slide. Okay, so now we'll do something symmetric. We'll put a differentiation operator to the view, and what we'll get back is the changes to the view. So if you remember the slide where we started from, we said we want a computation that starts from the changes to the database and gives us the changes to the view. This is the computation. You see, so if you apply these three operators in sequence, you compute directly starting from the changes of the database, you compute the changes of the view. So this is what we're looking for. This is the incremental version of the query. In this case, of a lifted query. So this is actually our definition of incremental view maintenance. Usually when people in databases talk about IVM, they stop here. They don't do the differentiation. They only want the stream of views. But I think this definition is better for several reasons. One is it's compositional, because these are changes and these are changes. So it means you can take multiple systems like this and chain them, and they will all talk the same language. And then I'll also argue that it's very interesting. If you just do this way, incremental view maintenance, you haven't done anything special, because you have to build the database, run the query, and then compute the changes. This is very expensive, but we can make it much more expensive. Once we know what we want to achieve, I will show that this block can be made much, much more efficient. Okay, so for example, there's a class of operators, queries that are linear. And if a query is linear, then the query is equivalent to its own incremental form. So it means you can just apply the query directly on the transactions. You don't need to integrate anything or differentiate. You get the changes to the view. And it turns out that most relational queries are built out of linear operators. So for example, filtering, I think is very intuitive for everybody. If you have a query which filters rows, you can only look at each row that you insert or delete separately. And if it passes the filter predicate, then it will be in the change of the view. You don't need to know what is in the view. You only need to look at the records themselves. That's what it means for a query to be linear. Okay, then there's a very surprising rule, which is the chain rule, which says that if you have a query which is complicated and you want to incrementalize it, you can then incrementalize each piece. So this might be very surprising, but it's actually really easy to prove. It's a proof by pictures. So that the top line is the incremental version of the query, which is the first query followed by the second query, and then the incremental version means you put an I and the D around it. That's what the definition is. And then what we do is, you remember I and D cancel out, so we sneak a pair of them on the middle arrow, and we just reassociate, and we get the incremental version of the left and the incremental version of the right. That's it. There's nothing else. So what this means is that if you have a language to write queries, no matter how complicated it is, the only thing you need to know is how to incrementalize the primitives. If you know how to incrementalize the primitives, you can incrementalize any query, no matter how complicated. And there's another class of operators called bilinear operators. Joins are a class of bilinear operators. Those have you have a question. So the question is about distributed. So you're asking whether some operation
So on your previous slide.
Yep.
I'm just wondering if you would call this operation distributive.
Yeah, I guess you could say that the incrementalization distributes over composition. You could say that mathematically. Yeah, and for binary operations, these are operations that distribute over addition, and joins are the most typical example. There's also a form which says, if you give me an operator and I want to compute its incremental form, there is an incremental form here. This might look complicated, but if you squint at this carefully, you'll see that actually this is something that people call the delta rule for joins, which has been known for a very long time. So this theory will recover that. And actually, I think I have enough time to explain how it works. It's not very difficult. So let's see. Let's consider the case of a Cartesian product. So we just do the product of two relations, right? And now we want to do it incrementally. What does it mean? I mean, we have two relations and we add the row to the left one. So what is the change in the output? Well, this row in the left relation has to look at all the rows in the right relation, right? And that's happening here in this. So this is the left change, and this integrator on top. This is an integrator. This actually builds the left relation entirely. So this the previous version of the left relation is delayed, is combined with the current row, the current change. And symmetrically, there's another one here. So if you add something to the right relation, it has to look at everybody in the left relation. And then there's another thing that combines everything, all the rows that show up in both changes. And then you just add them up. So that's how it works. It's very, very simple. But this side is much more efficient than this side, because this side has to do the join of two full relations. This actually does 3 joins, but each join involves only a change on one side. So this can be much cheaper. They do many more joins, but each of them is much cheaper. All right. So, maybe I was just fooling you. I'm trying to cheat my way out of this because I snuck in a point at the beginning, which is that this works only if the operations in the stream form a group. So plus has to be commutative and associative, and minus has to be the inverse of plus. So but databases are not like that. Databases operate on sets, and if you look at sets, there is no negative value of a set. So how do you do this on databases? And let me teach you another trick, which is a very, very simple trick. It's not our trick. It's been around for a long time. So how to convert a database into a group? So, database is SQL today operates on multisets. So a table can have duplicates. So if a table can have duplicates, you can say, this row is in this table 5 times. So now why not say this row is in the table minus 5 times? So that's what you do. For each table and for each row, you put a weight, which says how many times the row shows up in the table. And these weights can be positive or negative. And this is called the Z set. So the table is a set, but with the Z comes from the integers. These are integer numbers. So this is, you can represent any table this way. So now Z sets are very, very nice. They are like magic. They have several nice properties. So first of all, you can represent tables in a database using Z sets. A table is just a Z set where the weights are all positive. And you can have a represent multi-set using Z sets. Some weights will be bigger than 1. But you can also represent changes. A deletion is a row which has a negative weight. So not only tables, but changes, they are the same kind of object. So Z sets can represent both in one representation. As I said, both sets and Z sets can be sets and multi-sets can be represented using Z sets, but Z sets are richer than that. And just happens that the Z sets have form of commutative group. The way you add to Z sets is you find all the common rows and add up their weights. It's very simple. You think of them as a hash map, and you just look up the rows and add the weights. And if the weight is 0, the row is not there. Okay, so now, but databases are databases. They work with sets, not with Z sets. Well, it turns out that this is you don't have to see this. It's very small font. I'm just trying to make the point that everything you can do in SQL, you can do using Z sets. So if you give me, selection, filtering, projection, Cartesian product, joins, intersection. Each of these I can write using a few blocks, which are z-set, computational z-sets. All right? And if you have a complicated query, I can break it down into subparts. I implement each subpart and I just soup them up. So it's recursively defined on the query structure. You will see that many operations require this block label distinct. This is exactly because database usually operate on sets. So if you want to get a set at the end, you usually have to apply a distinct. But everything which is not distinct in this picture is linear or bilinear. And remember, these are really, really efficient incrementally. So if you have these operators, they are very, very cheap. Distinct is not cheap, but actually we know how to do distinct incrementally cheap too. And this is just the relational algebra, but databases go behind the relational algebra. They do group bys, they do unnests, the modern ones, they do aggregations, they do recursion. All of these work in this model. So there's no problem to simulate any of these in this framework. So they all can be built this way. Okay, so now this is a one-page algorithm which will solve the problem we set on the first slide. I have a query, I want to build the incremental version of that query. So the way you do it is the following. Step one, you build a query plan. If you have any compiler for your SQL, that will build your query plan. So this is just a normal query plan. Then you use the rules in this table to make the query plan work on Z-sets. Okay, so the query plan usually works on sets, but you can implement it on Z-sets. In fact, in our compiler, we use Apache Calcite. Calcite is a framework which was designed for normal databases. It works perfectly. So we use it for the first step. Then we convert it to compute on Z-sets. Second, then what you got is a query that computes on Z-sets. Second, you lift the query. By lifting the query, it now starts to operate on streams. But each value you supply, you'll get the number. So it's like the original lifted query that we started from. Then you incrementalize the query. How? Well, remember, to incrementalize the query, you put an integrator in front and you put a differentiator after it. That's what you do. And finally, you use this chain rule I showed is to simplify this plan that you got, and you get an optimized query. This algorithm is very simple. It's deterministic. There's no heuristics. Heuristics are before the algorithm. When you build the query plan, you can choose which query plan you want to incrementalize. For each query plan you incrementalize, you get a different incremental plan. And the cost is proportional to the query size. So it's a very, very simple algorithm. So let me show you an example. So we'll do this end to end. Maybe this will make it more concrete. So this is a simple query which has two tables, T1 and T2, and does a selection of filter and then a join at the end. So the first step is to build the query plan. So use any SQL compiler, any tool of your choice to build this plan. And this one has some selections, some distinct, some projections, a join. So don't worry too much about the sigmas and the pi's. These are standard notations in the database literature, but this is selection, this is filtering. That's all you need to know. Okay, so you build this. Now this computes on collections. So now what you do is you can remove some distinct calls. These are well-known optimizations in the database literature where distinct calls are also expensive. So it turns out for this query, you can push all the distincts to the end here. So you can compute on multi-sets and then make that into the set at the very end. And you get the same result. Okay, then we lift. So this is the plan we were on the previous slide. We had it on the previous slide. So when we lift it, what does it mean? It means that now we start to compute on streams. What used to be a collection now is a stream. It means we just feed it more data items, one after the other. And then all the operators are lifted, you see? So it used to be that this was a sigma, now it has an arrow in front. That's all. That's how you lift it. Everything gets an up arrow in front. Now we incrementalize it. To incrementalize it is very simple. You go out all the inputs and put an integrator in front. And then we go out all the outputs and put a differentiator there. So what happens? Now this is a different circuit. They are not equivalent. This circuit computes on tables. This circuit computes on changes. These are changes that you're going to stream. So that's the relationship. This is the incremental version of the previous circuit. So this is very mechanical, very simple. And finally, you start to optimize it. So you apply the chain rule, for example. The chain rule says that you can take each operator and incrementalize it separately. So you see the integrators are gone, but what the sigma has been replaced with the sigma delta. So each selection I incrementalize separately, each projection I incrementalize separately, each filter I incrementalize separately. And some of these are linear, right? So you can just replace them with the same operation. So selection and filtering happen to be linear. So you don't need to do anything special. So the only ones which are left in this picture are the join and the distinct. And these have some expansions. So the join you can expand, as I showed you, the distinct has another expansion, but in the end, you're left with this circuit. So this circuit takes streams of changes to the input code tables and gives you streams of changes to the view that you maintain. This is actually a streaming system. This is not a simple function, because these integrators, you see, it has some integrators, they have delays inside, and delays have memory. So this circuit is very sensitive to the order of the inputs. So you can't just start it in the middle. It will compute correctly based on the entire sequence it's seen. It will give you the correct content of the view. And this works for anything you can write in SQL or even in data. Okay, so Leonid, my colleague, will show you a demo. But before he gets ready, I will remind you, I have shown you 3 tricks. Each of them is very simple. And when you put it together, you actually get something very important. The first trick is to think of everything as streams. Databases are streams, transactions are streams, views are streams. They're just streams of snapshots, consecutive values. Okay, that's the first idea. The second idea is to define incremental view maintenance as a computation from streams of changes to streams of changes. And the third trick, which ties everything together, is to use z-sets. Z-sets give you this very nice and elegant object which has plus and minus. Okay, so we need plus and minus on tables. And z-sets are the object that gives you. And the z-set is nothing but a table where each row has a weight. Okay, so what is Feldera? Feldera is a little startup we created, and there's several of us here together to try to prove that this actually is not just nice boxes and arrows and papers for VLDP, but it actually is something that really is very useful in practice. And hopefully Leonie will convince you of that. Questions in the meantime while he's setting up? Yeah. Let's start from that side.
Without much context in the relational algebra, what are the differentiator of this new finding, or this?
So I'm not sure I understood the question. What about differentiator? You're talking about the my differentiator?
Yeah, compared to the de facto what they use.
So you're talking about how this differs from other models of streaming?
Yes.
Actually, many models of streaming are very close to this. So, for example, you could think of Flink as an assembly language in which you could synthesize some of these operators. But I don't think anybody has put them together in this way with z-sets, for example. They are very simple, but crucial ingredient makes everything much, much simpler. So people understood many of these aspects, but they work, and many databases like, Snowflake offers a streaming set of streaming operators. But if you read carefully, you see, when you do insertions for some queries, it works. When you do deletions, some queries don't work. So it has all sorts of restrictions. But this works uniformly across insertions or deletions and arbitrary queries. So there's no compromises in the title of the talk. Yeah.
When you have the stream of changes to the database, how important is it to analyze the stream of changes in the exact order that they appeared to find the end result of the computation?
Okay, so the question is, if you have a stream of changes to the database, should they be processed in the order they are applied? So in general, if you know that there's a legal stream of operations that is applied to your database, you can, when you convert it to Z sets, addition is actually commutative, so you can process them in any order you want. But first, you have to make sure that the stream is legal. So for example, a database doesn't let you delete a record that isn't there. Okay, so you can't just make it a -1 and say remove it from the database, because then you would get a table which has a minus, and that doesn't exist. So if you, after you validate that the input stream of input changes, then you can do them in other orders as well.
Does this limit certain class of operation that you can compute in this way?
So could you repeat the question?
Does this limit the class of operations?
Okay, no, this doesn't limit. Well, so the fact that the input stream must be valid for the database that you want to emulate, but once you establish that, you can run any arbitrary query, implement it in this way. So there's no, it doesn't constrain. In fact, it gives you more freedom than a traditional database. You can do some optimizations the database can't do. I'll be happy to talk offline about. We'll stay here after the talk.
Thank you.
Yeah, just have one question. It made sense how you lifted most of the operators, but how do you lift the distinct? Because then you're converting it to a set, and like, isn't it possible that you don't know how many you're reducing, and like maybe simply just run out of elements for you?
Okay, so the question is, distinct is a crazy operator. How do you incrementalize distinct? So first of all, lifting an operator is very easy. You just apply it to each input that comes separately. What we want is a distinct that is incrementalized. So when it sees a change, it has to tell you what changes in the output. So it's a very good question. Distinct is tricky. So why is distinct tricky? So think about this. Let's say you have a set, and then you insert an element which is already there, right? What is the output change? It's nothing. Because when you distinct a set that has twice a copy of an element, there's no change in the output set. It's the same as the original set. So distinct, like join, has to keep internally state, and the state is the whole set it's seen so far. So remember, the join had an integrator. It uses that integrator to remember the left and the right inputs, so it can combine them with whatever change comes on the other input. So distinct is similar. It keeps the whole input so far. And when it gets a new change, what it does is very simple. It looks to see if the change exists already in the input. And if it's in the input, it looks to see if the weight goes from negative to positive or from positive to negative. These are the only two cases. So the point is, the work it does is only proportional to the size of the change. It has only to check the elements in the change. It keeps the whole input, so memory usage is big, but the work it does is small, is only as many as elements in the change. And for each of them, it can decide whether they are in the output or not.
All right, thanks. So what Mikhail just told us is that we have an algorithm that allows us to take any SQL query and run it in streaming mode. And I mean, literally, not some kind of subset of SQL, not some kind of weird dialect, complete standard SQL with standard semantics and strong consistency. And I don't think there is a system out there that quite does this at the moment. So we decided to build this company, Fildera, to kind of prove that this works. So this diagram is probably very familiar. This is what Flink and all these other systems look like, in that they ingest a stream of changes from your data lake or lakehouse or one of multiple kinds of streaming sources, Kafka, API, databases, and so on. They evaluate SQL in it, and they output back into the same kind of sources and destinations. The difference is that the SQL inside is the same standard batch SQL that you use, with your databases. So the way we describe it is, if you cannot run your SQL, it's a bug. All right, so let me do a live demo. This always go well. Okay, so we're going to do a textbook example to kind of illustrate what Mikhail was talking about. So we have this simple database. We have a table of warehouses. We have a table of products, and and we have a table that tracks how many items of each product are available in each warehouse. And just for the fun of it, we're going to compute the total volume in cubic feet of all the items in each warehouse, right? So we wanna join these input tables, group by warehouse ID, aggregate, and then do top K, which in SQL is order by limit. Okay, so let's do it in Cloudera. Oh, great. Okay. All right, so actually I already built this pipeline here. So let's look at the SQL code. So like with any SQL database, you start with defining your tables. So we have our warehouse, our product, and our storage tables. And then we define our queries as views on top of those tables, right? So for example, there are a bunch of views here, but this is the one I was talking about. So the first view where we join and aggregate our tables. And then we use this view to build the next view, which computes the top K, so order by limit. And this is very simple, but one thing I want to emphasize is that we allow you to build these multiple views and stack them on top of each other, which might be an anti-pattern in normal databases. But we actually encourage you to do a lot of this because this is how you build very complex analytics out of small building blocks. And the end-to-end latency is still going to be very low. So this is going to run all of this in streaming mode with low latency. You can deeply nest those views. Okay, so this so far looks like normal batch SQL. Of course, we're going to run it in streaming mode. So for this, we are going to build a streaming pipeline where you start. So this is your program in the middle. On the left are the tables, your inputs. On the right are the views. Okay, and so to run the program, we need to connect your streaming data sources. In this case, we have a bunch of Kafka topics pre-filled with some data. So we're going to connect to those to our input tables. We could also be streaming outputs back to Kafka, but this time I'm gonna just look at it in the UI. Okay, so this pipeline has been already running for some time. We have some data. So in fact, let me stop the pipeline so we can look in slow motion at what's going on. So it has ingested some data, and we already have our winners. So we have the three warehouses with the biggest volume of items in them. Okay, and now I'm going to use our REST API to populate the first warehouse number one with I think 100 million, some large number of items. So warehouse one, product ID one, some millions of available items. Okay, I don't know if you noticed, but the view has just changed. So our warehouse number one now contains this huge volume of goods that probably wouldn't fit in a real warehouse. So this is incrementally maintenance, right? I change the input and it instantly incrementally recomputed the view. Okay, now what happens if those changes arrive in real time to the stream? So I'm gonna unpause the pipeline. Okay, so now we have incrementally maintenance just running really fast. And I hope this kind of drives home the point that Mikhail was making, that IVM and streaming analytics are really two sides of the same coin. If you have a really efficient incrementally maintenance engine, then you have yourself a streaming analytics system that can handle all of the scale. Okay, now the truth is, oh, that's because it's absurd. So in this particular use case, it's absurd. So the next time I wrote a volume of item number one, it overwrote what was there before. Yeah. But good observation. Okay. Now the reality is that nobody cares about updating their warehouse inventory in real time. So let's kind of outline a more realistic and useful use case for Cloudera. So one of the places where people really care about doing real-time analytics is real-time feature engineering. So in real-time feature engineering, if you're not familiar with it, you have a real-time stream of events. Could be IoT data. In this case, it's credit card transactions. And we would like to use machine learning on this data to identify, in this case, fraud. Okay, now if we feed this raw data to ML, it's not going to do anything useful because we just don't have enough context. So what we want is to compute various statistics on the entire history of this data and feed those stats into your ML model. Now, this data enriched with those stats is actually useful input for ML. Okay, so if you think about this query that I just mentioned, where we want to, did I mention? Okay, so what we want to do is we want for every input record, we want to look at, for example, 1 month's worth of transactions and compute an average or a max or a standard deviation. And you can do it in SQL with this kind of over query where we partition by a credit card, order by time, and then look at a time window. But this is not an easy query to evaluate incrementally, right? Because if you think about what we're doing here, it's not a tumbling or hopping window. For each record in the input stream, we define a different window relative to this record, and we aggregate within this window. And you can, I guess, intuitively say that you should be able to reduce computation reuse computation between those different windows. But especially if you have out-of-order data, it's actually not very obvious. And the data structures and algorithms you need to do that are fairly complicated. And without diving into details, the reason we can do it efficiently is DBSP, the theory Mikhail was talking about, because it gives us a very well-defined structure to define what exactly it means to build an incremental operator, to build them modularly. So, if you build a correct implementation of an operator, it will work with everything else. And it gives us nice primitives like the Z-1 operator to actually build those circuits. I'm almost done. Well, in fact, I'm pretty much done. So let's see if my laptop survives running this pipeline. But yeah, I don't think, I'm not aware of any other streaming engine that can do these queries efficiently. I apologize to any streaming engines that can actually do it well if we got it wrong. But so yeah, so this is running my laptop, processing about 100K records a second while computing a bunch of this like heavyweight rolling window kind of aggregate. All right. So that concludes the talk, and Mikhail and I are happy to take questions.
So I will ask one of the questions coming from our remote participants. I will actually combine the question of two people for the sake of time. Question from Raghav and Shin are, what do you think are the performance trade-offs between using a system designed specifically for incremental updates like Caldera versus a more general purpose stream processing framework like Flink? And as a follow-up, any benchmark test in typical production queries demonstrate its advantage, throughput, performance, etc.?
Okay, so the first one is Flink, Caldera versus a general purpose framework like Flink. I'm not sure what makes Flink more general purpose. Probably it's about the fact that this is not, this is SQL, and Flink also has a different API. I think this is a general purpose framework. So DBSP is a general purpose streaming analytics framework. It lets you do all kinds of things that are not just SQL. And we could be building additional front end. Yeah, I think this is streaming analytics that is done correctly. What was the second one?
Any benchmark test in typical production queries demonstrating its advantages in terms of throughput, performance, etc.?
Yeah, so we haven't published official benchmarks yet. So on our website, there are some benchmarks, Caldera versus Flink on Nextmark, where we outperform Flink significantly. But again, we need to do a bit more work before we can publish, official framework benchmarks. Do you want to add something?
Yes, so when you compare, you have to be sure you compare apples to apples. For example, fault tolerance must be enabled, checkpointing. So it's easy to tweak a system, but we have to be very careful before we publish the numbers.
I'm just gonna think of the question right now. But basically, you showed the sinks that were. You showed Iceberg, Delta Lake, and I think maybe you had Hoodie there too. Are these like connectors out of the box that you guys provide on Caldera, or what's the integration process?
So we have Delta Lake connector out of the box. Yeah, I think it's just been merged. We are still building the other ones.
I think we're at time. Thank you very much for the presentation. So now for Voltron data, please connect your computer. So now we're going to hear about Ibis, the portable Python Dataframe API. And the presenters are Philip Cloud, who is a principal software engineer at Voltron Data. He works primarily on Ibis, a portable Dataframe API for Python. He has done different things over the years, from jazz drumming to cognitive neuroscience, and naturally he wound up working on software libraries. You can find him on GitHub and the Ibis Zulip instance. And Chloe has a background in data science and started working on streaming systems as a founding engineer at Claypot AI, a startup tackling challenges in real-time machine learning. She led the infrastructure development of an open source real-time feature engineering platform and worked on the translating and optimizing streaming workloads that served low latency use cases. She brought her streaming experience to Voltron Data, where she leads the development of Ibis streaming.
Hey everyone. I'm Philip Cloud, and sorry. Let's go back to the title slide. We're here to talk about Ibis, a portable Python data frames. We are. I'm Philip Cloud. Been working in the Python analytics space for over 10 years, mostly on open source libraries like Pandas. I am the tech lead for the Ibis project at the moment, and I work as a principal engineer at Voltron Data. This is my colleague, Chloe.
Hi, everyone. Thank you guys all for staying. I know it's all past dinner time. I was a founding engineer working with Z over here and some of my coworkers over here at Claypot AI. And Claypot was acquired at the beginning of the year. And we are now a part of Voltron Data, which is very exciting. I'm right now a senior engineer at Voltron Data. I've worked on infrastructure for real-time machine learning at Claypot, and now at Voltron Data, I work on Ibis streaming.
Sweet. Okay, so what is Ibis? Ibis is a Python library for a few different things: exploratory data analysis, general analytics, data engineering, ML preprocessing, library. You can kind of use it as a library. You can kind of build your own version of it if you want. And the idea that it sort of, I think, brings to the table is the ability to take your code that you're writing for development to production without very many rewrites. Let's look at some examples so we can kind of get a feel for what the library looks like. So let's see where my mouse is. Okay. We've this is sort of it's pretty simple. Import Ibis, load up an example. Here we're looking at this Palmer Penguins data set, and this is sort of the default representation of a table you get. Now, if you want to look at some aggregations, do a group by on species and island, count some stuff, average some stuff. Again, kind of simple group by. And then you can get into some slightly more complicated stuff. Here we're using a dictionary, and we're kind of running over all the numeric columns except for year and subtracting the mean. And there's like a slightly more concise way to express this, but this is sort of generic Python code. It's pretty familiar. So We left it as is. Ibis kind of nominally generates lots and lots of SQL. It also operates on other things, but what does that sort of look like? So we took this sort of original expression here that we had in the previous slide, and like it produces some pretty nasty SQL. And once you start adding, I don't know, dividing by standard deviation, doing more complicated things, it gets even worse. So it's like, okay, what's going on here? Let's get back to our examples. What else can you do with Ibis? This is an end-to-end analytics application that we use to track our metrics like GitHub stars and other things that people care about. It is it's a Streamlit application. It's got all sorts of goodies, and this is something that is built with Ibis, and this is actually hosted on our website, or rather, it's embedded in our website. This is the link you can go to and see the whole thing. But it is all the code here is written. All the queries are written using Ibis. Yeah, lots of fun goodies and things to look at here. We'll show some other code later as well. So like why did we build Ibis? Sorry, my laptop's not remaining on the stand. All right, I'll just hold it there. Right, Dataframe. So who's heard of Dataframes? Okay, so a few people. Bit of quick history. Dataframes actually come from the S programming language. Has anyone heard of S? Okay, so like 3 people, 4 people. Okay, so if you've ever used R comes from S. Moving right along. Pandas sort of, perfects the data frame in theory. And then like, there's just an explosion of Python data frame libraries. Pandas sort of becomes the de facto standard. It still doesn't scale. And then like, you kind of have this problem where people are throwing code over the wall to engineers and say, hey, like write my thing in a thing that we're going to use in production. Like, I don't know, Java, C++, whatever. Just not, pandas. But so like, what if Ibis were like a new standard? And so the legal department definitely required us to put this slide here. It's the I guess it's now sort of cliche, but yeah, I don't know, add a standard and then you've got another 15th standard. Oh, okay. Cordo mistake. So this is sort of the origin of Ibis. Like Wes McKinney created it. Wes created pandas, and the whole point of Ibis was to kind of bring portability to data frames. It started with Impala, then grew sort of Postgres and SQLite and a bunch of other things. We've got like 20 or something backends now. And that's sort of where Ibis comes from. So again, it's this two-world problem. You've got SQL, which has databases and tables and analytic metrics, dashboards, and then Python sort of has this scrappier sort of like, okay, we've got files and like things in memory and statistics and notebooks and like, so never the twain shall meet. But Ibis kind of bridges that gap. And so how does it bridge that gap? Well, basically the code that you write stays the same across all these backends. You've got DuckDB, Polars, Data Fusion, and you notice there's some SQL things and some non-SQL things, mostly SQL things, but Polars is not SQL. Trino, Flink was added recently. There's more, but these are sort of the first ones that kind of came to everyone's mind when we were making the slides. So how does Ibis work? This is going to be kind of fast, but happy to answer questions. All right. So some themes in engineering the library: immutability, type checking, separation of concerns, extensibility. Focus a lot on end user experience, avoiding the common denominator trap, which I think is common with projects that are like, hey, here's a bag of adapters to like turn A into X, Y, and Z. We also like for Ibis to be able to scale up and down. A lot of like frameworks for interacting with big systems feel big, and we kind of want Ibis to not have that feeling. The main components of Ibis is an expression system. So you've got some columns that represent string scalars and integer columns, and on those things you've got methods like split and join and sum. Those things don't have any knowledge of their specific operation. They basically have methods and types associated with them. They hold an operation, and that operation is the specific thing that you're going to do, like split or left join, etc. They hold their inputs and an output data type and a shape like column scalar. And these are the things that we use to dispatch the compiler, like, sort of visiting different methods based on the type. What else? There's other stuff which I'm not going to go into, but is kind of neat. We've built a small type system in there. There's a fairly sophisticated pattern matching engine and some fun graph universal stuff. The main goal is basically to separate the API from the implementation with this particular design choice. So this is runnable Ibis code that if you run, you will get this particular graph as output. And it's showing you a graph of it's showing the expression graph. So you've written your aggregate, it's grouping by a field, and then you're taking the average of another field, and this is all coming from like the sort of leaf database table here. So what does it look like to compile this thing? We start with this, we topologically sort it, and then we do a bunch of stuff to that. And that's sort of not actually magic, but this seemed like an appropriate place to put this GIF. Effectively, what happens is for each node in this graph, we build up a dictionary that contains a mapping from the input node to its compiled output. We kind of accumulate that until we get to the final node. And then there's this sort of hidden box here, which is doing quite a lot of work. And that's our use of this library called SQLbot, which is a fun library that everyone should check out. As at some point somewhere in this process, we're doing some rewrites. There are backend specific rewrites where we can take operations from. We can kind of rephrase operations to work on a certain backend that may not have a particular piece of functionality. Yeah, that's how the compiler works. And then we sort of just chuck that SQL at whatever database we're using. We have like a SQL string at this point, and we kind of just send it to the DB API. There's a lot more happening here, but don't want to finish on time. And then we heavily massage the output. So some databases, for example, are able to give us like a nice format, like Apache Arrow. Some databases give us a string back. Some databases give us a list of tuples. It's kind of all over the place. Okay, closing and talking about streaming now.
Okay, I was just wondering if you can see the slides on the computer screen, but it turns out you can't, so no worries. But obviously we're here at a streaming meetup, so what are we going to talk about next? We're going to talk about how streaming plays a role in all of this Ibis stuff that we just talked about. So streaming plus Ibis plus streaming is relatively new. It's very exciting. It's something that we have spent a lot of time working on. So I'm very excited to talk about this today with you. You guys are on a streaming meetup. You all know that streaming has grown a lot in the past 5 years or so. If not, now you know. So over 70% of Fortune 500 companies have adopted Kafka, which shows strong growth in streaming overall. And a lot of these stats are actually a bit out of date. So I would imagine that actually a lot of companies and a lot more companies are today using Kafka or Flink or Spark streaming, so on and so forth. So streaming is becoming increasingly more and more relevant, which is also why we see a lot of people trying to get into streaming. There are data scientists getting into streaming, and so there's a lot of use cases that we're seeing with streaming today. This is a very, very, very simplified diagram of an architecture that you might have in your company. We spent a lot of time at ClayPod AI talking to companies, understanding their use cases, understanding how they were using streaming engines. And this is sort of what it boiled down to. So you have data, you have a batch processing pipeline, multiple batch processing pipelines perhaps, and you also have your stream processing pipelines. And at the end of the day, all of that feeds into some kind of downstream pipeline transformation, storage, whatever, right? So this is a very, very simplified process. A lot of times you may have seen some of these engines before. For example, Flink, like the DoorDash slides, they were talking about Flink and Spark, which is actually something we've seen with a lot of companies. So Flink being the de facto streaming engine that people are using today, and Spark being the de facto batch processing engine that people are using today. However, we also see that there's very exciting evolutions and a lot of new engines coming out all the time. So we are using Flink and Spark today, but you can talk to a lot of companies out there. You have probably been evolving this architecture over the years multiple times. Maybe you didn't start out using Flink and Spark. Maybe you started out with one of them, now you're using both of them. Or maybe you're looking to switch to something else. So a lot of this in the process is also you don't want to lock down into specific vendors. So this is a lot of the motivation behind what we're going to be talking about. So in the future, you want to be future looking. You want to have that extensibility and be able to switch to something else. And that is exactly what we're here for. In the machine learning world, you will see something like this. And when we were working on real-time machine learning at ClayPod, this is a very familiar process that a lot of companies were working with. A lot more companies are getting started with machine learning use cases and are getting familiar with the pain of this process. So you have some kind of production data coming in, very likely a stream of data. Your data is not coming in batches. So you're receiving your production data in some kind of a stream, and you are actually taking a sample of that data, making it into a batch, very often a CSV file. You're handing that over to your data science team. Your data science team is doing some kind of local experimentation in their notebooks. So I was a data scientist. I was doing a lot of this. As a data scientist, I was doing experimentation using pandas, using PyTorch, so on and so forth. You're doing this experimentation locally with a limited set of data. You're iterating on the model, iterating on the features. Once you reach a production-ready model, you are going to throw this over the wall. Throw this over the wall to the production team. So the platform engineers, the infrastructure engineers, all of you guys out here, you are handling actually the productionization of that code. A lot of times you're rewriting that code, you're rewriting the features for that, but that is beyond the responsibilities of a lot of times the data scientists like us. A real world example of what this looks like. This is an example feature of a window aggregation, which is something you often see in feature in machine learning models. So this is a very, very simple one. Actually, it's just a clicks data frame. You're calculating the number of clicks for each user in a 1 hour window. So this is how you would write it in your familiar Pandas API. When you're productionizing this, so here is an example of what this code looks like in Flink SQL, but you can be using any of the other APIs as well. So there is, the Java API, there's the Spark Dataframe API, there is the Spark SQL API. There's so many different APIs out there, and you can be writing a lot of different code rewrites depending on what your architecture looks like. And here you can see the code actually looks quite different, right? So you're rewriting all of that code. This expresses the same thing. The SQL is a little longer than what Pandas API looks like. And the code rewrite, as we have seen, does not just happen here. It happens from batch to streaming. For example, if you're just working with local experimentation, you may not even be doing these windows. A lot of times you already have your whole data set, it's bounded. So you can run your windows over the entire data set. And it doesn't have to be about, it doesn't have to be capped on a specific time period. Where when you're turning these features into your streaming features, you will have to consider that you're not going to be running most of the times, you're not going to be running continuous long-running non-ending windows aggregations on top of unbounded windows. So that's an example of batch streaming code rewrites, local experimentation to production. So sometimes your features, the specific type of feature you're using may not even exist in the specific platform. Like Spark SQL doesn't support specific over aggregations. There are certain limitations that you have to consider in that transition process. And this is a more niche and smaller subset of the companies that we have talked to who are struggling. But as more companies are starting to get more into machine learning, we'll see that people will be familiar with the pain of backfilling a streaming feature on a batch backing table. So perhaps you have a streaming data pipeline, but now you are developing new features and you want to actually go back and calculate the feature values for these features on historical data. And that is your historical data is stored in a batch storage somewhere. So you're going to be rewriting that streaming feature into the logic in your batch backing table. And a lot of other cases that I'm not going to cover here, but you get the idea. The code rewrite happens everywhere. And the solution here, you probably are already saw a hint of where I was going. And obviously, this was being talked about a lot today, which is very exciting. It means that a lot of people are experiencing very similar challenges. A stream batch unified API. And we have seen, this is not new. This is not a new concept at all. We have seen a lot of attempts going in that direction. You see a Flink SQL, which is actually quite successful. A lot of companies, especially a lot of companies in China, have adopted Flink SQL. You see the use of Spark Dataframe API, which is also a direction in this, a foot in the same direction, a step in the same direction. So you actually see a lot of solutions out there. What these solutions do not cover, however, is that these are still batch, or these are still engine specific. So you're doing it for Flink once, you're doing it for Spark once, and then you have to do the same thing over and over again for every single one of your engines. Every time you switch engines, or every time you're doing some kind of, a lot of times companies maintain separate pipelines, a Flink pipeline and a Spark pipeline. So you're at least still doing twice of these things. And this is the solution that we came up with. We were thinking, given that Ibis already was doing this in the batch paradigm, it was already trying to bridge the gap between different batch engines and trying to standardize across the different batch engines. Why not expand it so that it also covers streaming use cases? And this is when we went to Ibis and we were sort of thinking along the ideas of, oh, maybe Ibis can be something that would unify the stream and batch APIs. So this is how this code could be rewritten using our Ibis API. As you can see here, this is relatively shorter, so you're just doing an over aggregation. This is again a very common operation that you have. Oh, by the way, I think we forgot to mention that the QR code leads you to the slides, so you can also follow along with the slides or go back and read anything that you missed. But even though I've talked so much about stream batch unification, and so did other people, why is it that we haven't sort of reached a conclusion yet? It's hard. Creating a stream batch unified API is hard because we've been there. Streaming is very, very different. The way that people talk about streaming and batch today is still sort of as two separate paradigms. We do have this hope where we are going to go with the community to push towards the direction of unifying both. But today, the way that people are looking at streaming and batch is still that streaming is different. We have to worry about time semantics. We have to worry about long-running queries. So a lot of times you cannot directly retrieve your results into an in-memory data frame like pandas. You cannot just get your output in a CSV. There are sources and things that you have to consider. So there's actually a lot of specific terminologies and architecture setups that you have to consider for streaming use cases. There's also less established standards in streaming syntax overall. So they're having a lot of evolution in both Spark SQL and Flink SQL and Spark Dataframe API. And you see that we're sort of going towards convergence, but there are still a lot of fluctuations in the development of these streaming APIs, and there's just simply less established standards. You can look at, for example, window applications. It's done differently in every single engine. And I know this because I'm implementing it right now. Today in Ibis streaming, Flink, we have two streaming backends. So as Philip has shown, we do have the Flink backend, which launched in Ibis 8.0 at the beginning of the year. We also have the Rising Wave backend, and I think Rising Wave is here too. Very exciting. These are two of our streaming backends. We were able to work with the community and introduce watermarks, window aggregations. These are some of the main operations that people are using in a lot of the streaming jobs. So we have sort of tried to work towards reaching unified API across different engines and across especially streaming and batch. And what is next? We are expanding the support of more and newer streaming operators and syntax. We are continuously iterating on this unified API, and Ibis being an open source project, you guys are all welcome to try it out and let us know what you think about the API, what you think about the project. And we have more streaming backends coming. So Spark being a major one that we will be launching very soon. And a lot of companies are outside of using Flink. Spark is also one of the major ones that people are using. And we're also looking to add additional ones. The recent refactor of Ibis has made it very easier to add your backend. So if you're interested, you should add an backend too. And all of this to wrap up all the talk that we've given on Ibis and streaming. A very exciting part of where we're going towards with Ibis is towards a composable data system. So if you haven't heard of the phrase composable data systems before, you may want to read this paper. It's a very cool paper. This paper was co-authored by some Meta people, Wes McKinney, who was the creator of Pandas, and some other people I can't really see from here. But this is a very cool paper. It talks about the composable data management system and exactly how Ibis fits into this picture. So the composable data system is basically saying that instead of you getting a data system complete, built for you, companies are starting to build individual components or sort of assembling them together as Lego sets. So that's the trend in industry that we have seen in the past 2 years. And there has been a lot of very exciting developments along this route. And exactly how Ibis fits into this is that you can see here, very typically in your data system, you will have a user interface, an execution engine, a data storage, some other things in the middle as well, depending on the data management system that you have. But Ibis is exactly trying to build this user interface for the data systems. So this is how Ibis fits into the picture, and we're very excited to see more developments, more contributions and community work towards a better, more composable data system. And giving it back to Philip now.
Okay, well, that's the demo. No, I'm kidding. Okay, so there are a couple ways you can try Ibis. This is like the pretty vanilla way. Pip install the thing, then try and run some stuff. Cool. That's not very interesting. We do now have Ibis in the browser, which you should immediately use for all of your production code, as with any double grimace emoji demo, it goes. This is a recent thing we have on the website. It's definitely not on the front page. If you try to look at it on mobile, iOS, anything, it breaks. So, don't do that. But this is like a Jupyter Lite terminal. I mean, I can't really do stuff with one hand, but okay, I'm gonna type out the world's slowest group by. No, I don't even talk. So that's like, this is like the world's most complicated group by engine. Anyway, that's the demo. You can go to the website and like go to this slide and try it out, or you can go to ibis-project.org/REPL and this will show up probably. Yeah, anyway, this is like, it's running WebAssembly, yada, yada, yada. There's a lot of complicated stuff in there. It's cool. Check it out. I think that's it. Go to the next slide. Okay. You can find us on all these places. These slides are up on the website under the presentations page. And yeah, that's it. Happy to take questions.
So we have a question from Yi Pan. How does Ibis deal with the semantic differences between stream and batch SQL? For example, Flink SQL streaming has watermark/emission policies to trigger a real-time calculation of a result, while batch does not have that.
Yes, that is correct. So there are certain things that certain APIs are only available on the streaming engines right now. So there are things that we're trying to achieve more unification, and you can sort of see a more unified experience, so that you can see a more unified experience across the different engines. But things like watermarks, you really can't introduce that into batch engines. So that's something that we only have on the streaming engines right now.
Thank you. Next question is from Stuart Schmackler. Why not use Apache Beam?
Great question.
Just yeah, it's hand the hot potato over, I guess. That's a good question. Well, so there's probably you know, an ad hoc reason I could throw in there, but I think it was because originally Ibis only worked, it was designed to only work with Impala. So I don't know if Beam was around in 2000 and I don't know, something teen, 2013, 14, 15, somewhere around there. So that's probably the actual reason. You know, I don't know if that's what Wes would say now, but I think that's the reason. It's not a very interesting reason.
I like the idea of taking the local code and be able to run in production. With doing that, with not rewriting it all, are there any efficiency concerns or any way to tell or assess like, oh, this type of query we maybe wouldn't want to do that. We actually need to get inside and do some fine tuning or something.
Not sure about the second, but I definitely have, yeah, we can definitely talk about the first. So we do a tiny bit of optimization. We do like simple select merging as one of the, I don't even know if I want to call it an optimization. It's like too simple to call it that, but most of the time, in fact, I don't know if we've ever encountered a case where we were able to see the SQL that Ibis generated being like meaningfully slower than like an equivalent handwritten query. Especially with some of the more modern analytics engines like DuckDB and Snowflake and BigQuery tend to have very, very good optimizers. There are cases where we like in our recent refactor, we did have a bug where we were sort of like doing way too aggressive inlining and select merging, and we generated like some ridiculously long SQL string with lots of, anyway, the engines had trouble dealing with that, but that's been fixed. Well, thank you.
Hi, yeah, thanks. So I was actually heard about it at my current company from another person who recommended it to me. Cool. And I thought it was a really interesting idea, but how would you talk about the problem? Like, so I feel like it's something that not that many people may have heard of, like compared to like Beam or something. So it's like another layer of abstraction. So you're trying to introduce, like, I don't have a problem with it itself, but you're trying to introduce like a new technology, a new language, like a new syntax.
Yep.
And I feel there's a lot of friction there in regards to whether, like me personally, whether I would choose to adopt it. Because if someone takes my position, they start doing it, like, then they might say, like, you know, like, why do I want this? Something, because to them it's some completely new, kind of obscure. Like, you know.
Yeah. So some trepidation around, oh, it's another layer of a thing, and yeah, sure, definitely have gotten some of that. If you like SQL, then Ibis is probably not going to be your favorite tool. We've definitely gotten feedback from people on the internet saying, "Hey, Python sucks. Like, let's just stick with SQL." Yeah, Ibis is going to be that thing. I will say that the amount of, I guess, abstraction is relatively small compared to a framework like Beam, at least at the Python layer. Ibis does have some additional abstractions for sure. At sort of at bottom, it generates a SQL string, and then it hands that to the database. So there's like a lot less machinery than something that it might be compared to. Yeah. Sure.
Yeah, so that's totally fair. And I would like to talk about how we at ClayPod got to Ibis in the first place. So we weren't initially working with Ibis. We started working with Ibis because what we were building was we were trying to build a feature engineering platform, and we're trying to turn user queries, the user written data transformation logic, into some kind of a query plan that can be optimized and turned into Flink workloads or Spark workloads or any type of workloads. And we're doing a lot of the optimization, the workflow optimization, workflow provisioning using a control plane for the user. So what we liked about Ibis is the fact that it separates the execution from the transformation logic. So you don't have to worry about how your transformation is going to be executed or understood by a specific engine. You just need to be able to express your specific data transformation. And that's really what we liked about it. And obviously there are extensions that you can do on top of that, which were also things that we were doing. But yeah, I think that's for us was a very convincing reason for us to start contributing. And that is why we built the Ibis Flink backend.
We also have or not many, but we have some APIs that are designed to like sort of let people dabble or get their feet wet without like being like, well, now I have to rewrite everything, right? So we have like a couple of methods like that are kind of .SQL where you can just like dump a SQL string into the back end and you get back an Ibis expression and you can start doing things from there. We have like we have another method called .SQL that allows you to like intermix SQL and Ibis. And you're just like, I don't feel like thinking about how to do this. Just run this query and then like I'll do some Ibis stuff after that, and you against a table that you've made with Ibis, so you can sort of freely mix them. And that's definitely designed for people who are, not yet sold. Somebody who works for Voltron Data wants to ask a question. Come on.
No, I actually don't want to ask a question. I just may share like slight experience, because I think the question of Apache Beam versus Ibis and other stuff comes up quite frequently. It's been a long time since I've used Apache Beam, but I think like a few things like Ibis, like if you look at them in a vacuum of like, oh, if I'm trying to unify across Flink and Spark, then sure, then Beam is like another alternative. But like if you're also looking to expand that to like local databases like FTP and a bunch of other SQL databases, maybe Polars, things like that, like that's a different use case. I think one thing which came up in the DoorDash talk earlier was the complexity of using Beam. Like at least I remember before, like writing all the like low-level P transform, like more like an RDD level kind of code. If you want to expose something to like a data scientist or like even like an ML engineer, or like maybe put some abstracted AP or like UI or API over it and to do like a query builder. Like I don't think you can really do that easily with Beam. Yeah, so I think like that's a couple of reasons why you might consider, or is a difference you might consider.
You should show people Ibis in the browser, but not on iOS.
All right. Thank you for the talk.
Thanks.
So I'd like to thank all our speakers for their excellent talks, and I would like to also thank all our participants today, both in-person participants and our remote participants from all around the world. So thank you for joining us on a weekday, making this event fun. We look forward to seeing you again in our next meetup in 3 months. So once again, thanks everyone.